Good evening, everyone. Welcome to the 7th problem solving session of the Computational Continuum Mechanics course. I'm Naresh. I'm a research scholar in the Department of Civil Engineering at the Indian Institute of Science. The topics for today will be mainly stress and equilibrium, and followed by discussion on work conjugacy, objective stress rates, and we'll also look at a little bit of principle of virtual work. So let us quickly get started. To recall what we have seen in the last problem solving session and also the coursework, to refresh, we can start with this. So the first concept is that of traction. So by definition, traction at a point on a plane normal to a given, on a plane with a given normal n is defined as the limit of the ratio of the force to an elemental area as the elemental area shrinks to 0, shrinks to the point itself. So you have a body, you cut the body with a plane, and this plane has got a normal n. And on this plane, at a point P, the net force per unit area, the force intensity at this point P is the traction at that point P. So the traction, to define the traction, we need to specify both the point and the normal to the plane in which we are looking at. Then you might have looked at the Cauchy tetrahedron analysis, which resulted in the relationship between traction and Cauchy stress. So traction and Cauchy stress. So we can always, traction is a vector, the normal is a vector. So the normal can always be expressed as N1 E1 plus N2 E2 plus N3 E3, where E1, E2, E3 are the basis vectors. It's an orthogonal system of, it's an orthonormal basis, and N1, N2, N3 are the components of this normal in this basis. So these are the basis vectors. And N1, N2, N3 are the components of the normal vector in these bases. In this basis. Proceeding with this, it is possible to express the normals, the traction on the principal planes, on the coordinate planes, which are, say, E1 is the YZ plane, and then E2 is the XZ plane, and E3 is the XY plane. So these are the principal coordinate planes, and on these planes, the traction can be expressed as a function of, as a linear combination of the basis vectors. So on these planes, you can always write the traction as some sigma 1 times E1 plus sigma 1 times E2 plus sigma 3 times E3. And further proceeding with this, you have sigma 1 times E1 plus sigma 2 E2 and sigma 3 E3. And the traction on the XY plane, which is normal to E3, is sigma 13 E1 plus sigma 23 E2 plus sigma 33 E3. So in a concise notation, so these sigma 11, sigma 12, sigma 13, these are the coefficients of the linear combination of E1, E2, and E3. Just a minute. So proceeding this way, establishing the equilibrium for a elemental tetrahedron located at the origin. Consider an elemental tetrahedron whose three faces are oriented along the coordinate planes, and one face and the other faces having a normal end with an area dA. So establishing the equilibrium conditions for this elemental tetrahedron and letting the tetrahedron shrink to a point, that is the volume of the tetrahedron, letting it to tend to 0, we recover a famous relationship between the traction at a point in a specified plane and the Cauchy stress at that point as follows. So the traction depends linearly on the normal vector, and the linear relationship between the two is given by a stress tensor. So the traction at a point on a plane with the normal n is equal to what we get in indicial notation is sigma ij ei ej dot n. So this ej dot n comes from projecting the area dA onto the coordinate planes. So its projection on the plane on the so let's call it 1, 2, 3. So dA1 is the projection of the area dA on the 2, 3 plane, and that is nothing but E1 dot n times dA. So you see where it is getting at. So this is how this factor ej dot n comes here. For more detailed explanation, you can refer to the lecture by the professor. So from this point, how do we proceed further? So look at this quantity ej dot en ei. We know that the tensor product of two vectors A tensor B acting on C is defined as B dot C A. Analogous to that, what we have here is ej dot n ei, and that should be just ei tensor ej n. Therefore, this becomes the traction at a point on a plane with a normal n is nothing but sigma ij ei tensor ej acting on n. But what is sigma I? So this quantity, which has got 9 components, sigma ij I going from 1 to 3, j going from 1 to 3 has 9 components, and these are 9 basis vectors, tensorial basis vectors. This is nothing but sigma n. So this is the Cauchy relationship. This is Cauchy's relationship between the traction on a plane with a normal n and the normal to the plane. They are related by this quantity sigma, which is a tensor, and this tensor is nothing but the Cauchy stress tensor. The third concept here is that of equilibrium. So translational and rotational equilibrium. Let me just. Now consider a very small elemental volume. So this has got a volume dB, or let's say this has got a volume V, and it is bounded by a surface dV. And there are tractions on this surface, which are T. These are the surface tractions. And on the volume, we have body forces, F. So this F is nothing but body force per unit volume. And T is the on B. And T is the traction, which is basically surface forces per unit area. So equilibrium requires that. For equilibrium, what do we require? The sum of all forces on this volume should be equal to 0 in the conventional sense. In this case, we have a distribution of forces as a volume distribution, which is F, and a surface distribution T. Therefore, the conditions of equilibrium are integrated over the surface. What are the forces acting on the surface? It is T dA. Let me use small a for the area. This is an elemental force acting on, this integrated over the entire surface, del V, plus the body force, the elemental body force is F dV integrated over the volume B. This should be equal to 0, which is a vector. Now use the Cauchy's relationship. So this is translational equilibrium. This is not the equilibrium of moments. As you see, this is just translational equilibrium, which is only the equilibrium of forces, not the moments. So we have established one of the equilibrium conditions, actually three scalar conditions. So this one vector equation is equal to three scalar equations, sigma fx0, sigma fy0, and sigma fz0. So this in turn results in sigma n from the Cauchy's relation dA plus f dV is equal to 0. Now, using the divergence theorem, you can use the Gauss divergence theorem, and convert this surface integral into a volume integral. So this n appears here. So whenever you have a normal and an area integration appearing, you can use the divergence theorem. So the sigma n dA is nothing but integral sigma ij nj ei. This is a vector. Sigma is a tensor, and sigma n is a vector, which is sigma ij nj ei. So you can check the indices. Both I and j are dummy indices, and the net result is a vector. And so the divergence theorem in a crude form, you can say whenever nj appears, you can replace it with d by dxj and replace the surface integral with the volume integral. So this means it is partial xj sigma ij ei dv. Ei is a basis vector which is independent of the spatial coordinate. Therefore, it is nothing but integrated over the volume del sigma ij by del xj ei dv. But this is nothing but, in a basis free representation, this is nothing but the divergence of sigma dv. So sigma itself is a tensor. The divergence of a vector is a scalar. Therefore, the divergence of a tensor is a vector. So what we have here, so this becomes a volume integral, and it can be clubbed with the next one. So this becomes divergence of sigma plus the force per unit volume, body force per unit volume, integrated over the volume, 0. But this V is arbitrary. So if a body is in equilibrium, every subset V of the body has to be in equilibrium. So the arbitrariness of this V results in the integrand itself being 0. So the condition for translational equilibrium is that del dot sigma plus F equal to 0. So this is a vector equation which is equivalent to three scalar equations, and this is equilibrium of forces. You can also look at the equilibrium of moments. So start with taking the moment of these quantities. So over the surface, the force is TdA. Take a moment of it about the origin. So on the surface, x cross TdA plus on the volume, it is x cross F dV should be equal to 0. So this is the analogous. This is exactly, there's no analogy. This is exactly the sum of all vector sum of all moments is equal to 0. So these two are the fundamental governing equation in statics. So starting with this, again, you can replace T as sigma n, which means integrated over the surface, x cross sigma n dA plus integrated over the volume, x cross f dV is equal to 0. Look at the first quantity. It is x cross sigma n dA. Write it down in indicial notation. It is integrated over the volume, epsilon ijk. The first vector is, so epsilon ijk is always in the cross product to get an ei. The first vector is x, so its components are xj. The second vector is sigma n, which has the components sigma kl, nl, and you have a dA. And use the divergence theorem. So use the divergence theorem. So what does it say? The trick to remember the divergence theorem is whenever you have an NL, replace it with partial XL of everything else. So this becomes integrated over the volume, dou by dou XL, epsilon ijk, ei, xj, sigma kl, dA. The permutation symbol does not depend on the position, nor does the basis vector ei. Therefore, this quantity is nothing but, you can take the permutation symbol out, epsilon ijk, ei can be taken out. You're left with dou by dou XL of xj sigma kl dA. And simplify, use the product rule. So this becomes epsilon ijk ei. We get, so this is dV, sorry. Once you convert it to a volume integral, this has to be dV. So here you get, first differentiate xj with respect to xl, which leaves you with a delta jl sigma kl, plus you have an xj dou sigma kl by dou xl dV. I can split the two terms now. So this becomes integral over the volume, epsilon ijk, the permutation symbol ijk, ei, delta jl sigma kl is has the, so Kronecker delta has the replacement property. In place of L, we can replace J. So you get a sigma kj dV plus integral V. We have an epsilon ijk xj dou sigma kl by dou xl dV. And there's an ei everywhere. So there's an ei. Let me put the ei here. Proceeding further, you get this integrated over the surface. So the left-hand side is this. What is the right-hand side? It consists of two terms. The first one is epsilon ijk sigma kj dV. First term is integrated over the volume. The permutation symbol sigma kj ei dV. Then look at the second term. What it is? You have epsilon ijk ei xj and something else. So this is what? This is basically the kth component of the divergence of sigma. So the second term can be concisely represented as x cross divergence of sigma. You can check it is exactly the same as the other. And you have a dV here. Now plug everything back into the first starting expression. Let us call this star. So plugging it back into star, you get integral over the volume epsilon ijk sigma kj ei dv plus join the two other terms. So here you get x cross del dot sigma plus x cross f dv is equal to 0. From these two terms, you can take, let me repeat the first term. From these two, x cross can be taken commonly out, and inside you get del dot sigma plus f dv is equal to 0. But what is del dot sigma plus f? This is equal to 0 by static equilibrium. Of forces. So this was the translational equilibrium condition, which means this entire term vanishes. So we are left with integral epsilon ijk sigma kj ei dv is equal to 0. Again, this volume is arbitrary, which implies the integrand itself has to be equal to 0. Epsilon ijk ei sigma kj is equal to 0. But this also means that epsilon you can, so epsilon ijk is nothing but minus epsilon ikj ei sigma kj is equal to 0. But k and j are dummy indices, so they can be replaced, which results in minus epsilon ijk ei sigma jk is equal to 0. Look at these two. We can add the two. So we get epsilon ijk ei sigma kj minus sigma jk is equal to 0. This cannot be 0. The basis vector itself is not 0. Therefore, the only way this can happen is sigma kj minus sigma jk is equal to 0, which means sigma kj is equal to sigma jk, which means the stress tensor is symmetric. Therefore, the Cauchy, the symmetry, can say that the rotational equilibrium or also known as the conservation of angular momentum implies the Cauchy stress tensor is symmetric. Right. So this was one concept. The next concept we are looking at is an equivalent statement for the conditions of equilibrium in terms of the virtual work done. So for a system of particles, we know that, so for a system of particles, you can say that a particle acted upon by several forces. Let us say the sum of all forces on the particle is just R, which is the residual. And if this particle has to be in equilibrium, this R has to be equal to 0. So the net force acting on a particle should be equal to 0. But this is a vector equation. This has got three scalar equations within it. So mathematically, this is exactly equivalent to the mathematically. This implies this dot product with the virtual displacement field. So you call, so R is a vector. R is the residual force residual. Del U is an admissible displacement field. This is an admissible virtual displacement of the particle. And since r equal to 0, by dot producting with any admissible virtual displacement, we are supposed to get only 0. So this is a scalar 0. This is a scalar equation. And this holds, when this holds for all, so r dot del u equal to 0 for all admissible del u, right? For all del u that is admissible. This is straightforward. You dot product something with a 0, you get a 0. But what is even more powerful is that when you take this del u to be arbitrary, when you allow arbitrary admissible displacements, this statement also implies the converse. So this is exactly equivalent to r equal to 0. Right? So this is in the context of classical mechanics. The conditions of equilibrium of a particle are equivalent to the statement that the virtual work done by the system of forces on any arbitrary admissible virtual displacement field del u is equal to 0. So the equivalence of these two can be proven if you take del u as 1, 0, 0, 0, 1, 0, and 0, 0, 1. So by doing this in some basis, if you take these vectors in some basis, it will corresponds to r1 equal to 0, r2 equal to 0, and r3 equal to 0, which are in turn, which is exactly this statement. Now in continuum mechanics, you can also arrive at something similar. So start with our translational equilibrium equation. What it is the divergence of the Cauchy stress plus the body force intensity per unit volume is equal to 0. Now dot product on both sides with an admissible virtual displacement field. So this is an admissible virtual displacement field. So let's do it. So this means and integrated over the entire volume, right? So this integrated over the volume V should be equal to 0, right? So let's do that. So it's integrated over the volume V, del dot sigma. This is a vector. Remember, sigma is a tensor. The divergence of a tensor is a vector. Dot producted with an admissible virtual velocity, virtual displacement field. Integrated over the. So this V is a vector V, and this V is the volume V. Let me use capital V for the. Let's do one thing. So let me use capital V for the volume. So we get the divergence of sigma dot producted with an admissible displacement field integrated over the volume plus the body force dot product with the displacement field, virtual displacement field integrated over the volume is equal to 0. Now this is a scalar equation because we have dot producted it with the vector field, which is del V. Now here again, look at this expression. Can start with the initial notation. What is del dot sigma? Del dot sigma is dou sigma ij by dou xj ei, but you are again dot producting with another vector field del v. So this is the ith component of the divergence of sigma, and the dot product is just del vi. So I gets contracted and you get what you expect. So you have this. This you can in turn express it as a sum of two terms using the product rule. So this is nothing but dou by dou xj of sigma ij del vi dv, right? Just take one term to the other side. So what is this using the product term? This is this term where the derivative is applied to the first one of the two factors plus another term in which the derivative will be applied to del vi. So that term goes to the other side. So you get a minus everything integrated over the volume sigma ij partial xj del vi dv. Now switch everything back to this. From initial, you can get back to the abstract notation. So the first term becomes integrated. So this volume integral can be converted to surface integral using the divergence theorem. So dou by dou xj will become nj sigma ij del vi dv minus integral over the volume sigma ij. What is the what is this sigma del vi del xj? Del vi del xj is nothing but the velocity gradient. So this you can write this as the velocity gradient Lij. But here you have this delta represents a variation or a virtual velocity field. Therefore, this is the virtual velocity gradient dv. Express it in get rid of the initial notation. So this becomes sigma n. Sigma ij nj is the ith component of sigma n. So this is the ith component of the virtual velocity field. So this you can write this one as a dot product of sigma n with the virtual velocity field dv minus integral over the volume. This is a double contraction. So this is nothing but sigma double dot plug everything back into this equation. And this is our integration over the volume. So this you can replace it as t, right? So this becomes t dot del v dv plus f dot del v dv is equal to this taken to the right hand side, you get sigma double dot del L. So let me write it down. So we get integral t dot integral over the surface t dot a virtual velocity field dv plus integration over the volume f dot the virtual velocity field dv is equal to integral sigma double dot del L over the volume. But note that del L has a symmetric part and an anti-symmetric part. So this is the rate of deformation tensor, which is symmetric. And this is the anti-symmetric spin tensor. So this is anti-symmetric. Minus, you have minus here. But sigma is a symmetric. Sigma is symmetric. Therefore, you know that sigma double colon del D is equal to this one exists. So sigma, let me say, so sigma double dot with delta L is nothing but sigma double dot delta D plus sigma double dot delta W. The contraction of a symmetric tensor with a skew symmetric tensor is 0. We can check that. Why? Sigma double dot delta W is equal to sigma transpose double dot delta W transpose. But sigma transpose is what? It is sigma, and delta W transpose is minus delta W, which means 2 times sigma is equal to 0. Therefore, this one is equal to 0. Therefore, finally, the principle of virtual work for a continuum can be written as integrated over the surface, the virtual work done by the tractions, plus integrated over the volume, the virtual work done by the body forces is equal to integrated over the volume sigma double dot delta d dv. The left-hand side is very clear. This is the virtual work done by the external forces, externally applied tractions and the body forces. And the term on the right-hand side are the internally generated stresses. So in concisely, you can express this as the net virtual work done by the external forces is equal to the net virtual work done by the internal forces, where the internal virtual work done is given as sigma double dot del d integrated over the volume. Now, this gives rise to the notion of work conjugacy. So, any two quantities, they can be some tensor, some force like measured T, double dot product with some contracted with some strain like measure, let us say some, say, call it some G, right? So, this is like a stress like quantity, and this is strain like quantity. These two are said to be work conjugate to each other if they can, if they obey this relationship. Basically, by taking the contraction of a stress-like quantity T with a strain-like quantity G, we recover the internal virtual work done, which is sigma double dot LD dV. If this is possible, then these two are work conjugate to each other. So this is a central idea in continuum mechanics, which says what kinds of quantity can be, what are the quantities, what are the allowed quantities that can get into a constitutive relationship. So you cannot just start with some arbitrary definition of stress and an arbitrary definition of strain and put them together in a theory, in a continuum theory. There are only certain quantities that are allowed, and those have to obey this work conjugacy requirement. They should be work conjugate to each other. Now let us look at some of the work conjugate quantities. We already saw that the Cauchy stress is work conjugate to the rate of deformation tensor. So this one defines a valid internal virtual work done. Therefore, one work conjugate pair is sigma and d. So this is a work conjugate pair. Now note that these two are work conjugate to each other with respect to the current deformed volume. So the volume that's appearing here is the dV. It's not the original volume. The equilibrium equations are established in the current configuration. Therefore, this is the current volume. Let me just see. But if we want to cast this with respect to the original volume, we can also make this transformation. We saw in kinematics that the volumes transform as dV is equal to J dV naught, where J is the Jacobian or the third invariant of deformation gradient. Determinant of F. Putting this transformation into this equation, we get integral over V naught dV naught. So in place of V, I'm putting J dV naught. And you have the same. This is still the internal virtual work done. So you can make some transformation. You can call this tau as J times sigma, and this is nothing. This is called Kirchhoff stress. So by scaling the Cauchy stress by the determinant of the deformation gradient, we get a new stress quantity, which is Kirchhoff stress. And the Kirchhoff stress is work conjugate the Kirchhoff stress is work conjugate to the rate of deformation tensor with respect to the initial undeformed volume. So this is important. After integrating, we get the quantities are equal. After integrating, we get the same internal virtual work done, because the internal virtual work done is a scalar that should not depend on uh, which reference you are using, whether you are referring to the initial configuration or the current configuration, because the virtual work done is a scalar quantity which should not depend on those. But the virtual work done per unit volume can differ. So the virtual work done per unit undeformed volume. So I'll put it in a different page. So the virtual work, internal work done per unit undeformed volume is not equal to the virtual work done per current volume or the deformed volume. So this is nothing but this is the Kirchhoff stress contracted with the rate of deformation tensor, whereas this is the Cauchy stress contracted with the rate of deformation tensor. So the Kirchhoff stress and the rate of deformation tensor are conjugate with respect to undeformed volume or the reference configuration, and these two are conjugate with respect to the deformed or the current volume. Right. Now, if you look at it further, we saw that integral J sigma double dot del D, sorry, del D. This defines an internal virtual work. However, there's a V naught here. This defines an internal virtual work. However, the integrand itself is having quantities such as sigma and D, which are spatial tensors. So sigma takes in a spatial normal and returns a spatial vector, which is the traction vector, and D takes in a spatial D is a spatial gradient of this is the symmetric part of spatial gradient of velocity field. So velocity field is spatial, X is spatial, therefore this D is also a spatial tensor. It relates spatial vectors to spatial vectors. Therefore, this is not really satisfactory. So what we can do is make the integrand also in terms of the reference quantities. So how do we do it? Start with this definition. This is nothing but integral over the volume J sigma contracted with del D dV naught. But what is J sigma contracted with del D dV naught? It is J sigma ij uh, dij. We also saw that sigma, let me put a del. So sigma del D is nothing but sigma del L, because sigma contracted with del W is equal to 0. So this is integral V naught J sigma ij del Lij dV naught. But what is del Lij? Lij is partial Vi xj. So this becomes integral over the volume J sigma ij. Let us see. We don't need to get to this point. We don't need this. So there is this relationship F dot is equal to LF, right? We proved it in the last session. The material time derivative of the deformation gradient is nothing but LF. So what is L? L is F dot F inverse. plug that into this. So we get sigma ij, and in place of del Lij, we can write it as del F dot Ik F inverse Kg dV naught. Combine these two, sigma ij F inverse Kj is nothing but, so Kj is the common component, and they are in the second index in both the tensors. So it is nothing but sigma F transpose F in the second tensor transposed Ij. So this is integral with respect to V naught J sigma F inverse transpose Ik, right? J gets multiplied out. This is Ik. Del F dot Ik dV naught. So put it in the concise format, get rid of the indices. So we get integral V naught J sigma F inverse transpose, this entire thing contracted with del F dot dV naught. Now this has got a special name. So this quantity called P, which is the first Piola-Kirchhoff stress, this is conjugate to the rate of deformation, or the time derivative or material time derivative. Let me not put rate. It's the conjugate to material time derivative of the deformation gradient. So the second work conjugate pair that we have is P and F dot. So where P is nothing but J sigma F inverse transpose. Now, further, if you look at P, the first Piola-Kirchhoff is not symmetric. Right? You can quickly look at it. This is not a symmetric tensor. It can be made symmetric. It can be make it symmetric. How? This can be made symmetric by pulling the force back to the reference configuration. So let me tell you what it means. So note that you have this P acting on a reference area element. So this is a this is the first Piola-Kirchhoff. Suppose it acts on an area element of the undeformed configuration. What do we get? So let us call this force dP. This is a vector. This is a tensor. This is a vector. This is a vector area. What is this? This is nothing but J sigma F inverse transpose dA naught N naught. So let us collect the scalars and vectors in a certain format. So we get sigma J F inverse transpose N naught dA naught. What is this? This is the transformation of oriented areas. So this is the transformation of vector areas. This is nothing but sigma. This is nothing but the new area dA. But this is basically traction dA, which is the elemental force in the deformed configuration. So forces exist only in the deformed configuration. You can express it as acting per unit area, per unit vector area of the undeformed configuration. So this is basically force per unit area of the undeformed configuration. Now we can actually pull back this reference, this force, so that we can define a different force. Let us call it dP naught. Right? This is not a physical force. You are just pulling back the actual force per unit area, actual force to the reference configuration. So you are pulling it back. So pulling back operation is represented by this, if you have noticed it. And in this case, let us use the inverse of the deformation gradient to pull it back. So you get F inverse P dA naught N naught. But what is F inverse P? It is F inverse. I take the J is a scalar. J F inverse sigma F inverse transpose dA naught N naught. Now this quantity, if you look at it, it is symmetric. And this is called S. So this is also a stress quantity called the second Piola-Kirchhoff. So the second Piola-Kirchhoff stress is, it's what? We are first pulling back. So one operation is pulling back the elemental force to reference configuration. And then express it as a per unit undeformed area. So S is defined as this quantity, J F inverse sigma F inverse transpose, which is nothing but F inverse P. And this S is actually symmetric. So can we find a coordinate? Can we find uh, a work conjugate quantity to S? Yes. So start with this definition of S. S is equal to F inverse P, which means P is equal to Fs. We already know that P and F dot are work conjugate to each other. So this means P double dot del F dot. This is a valid work measure. In terms of P, substitute Fs. So Fs F dot dV. This is a work quantity. We want something multiplied with S, something contracted with S to be this. So let's take this F to the other side. So you can show, again, expand it in the initial notation and then make some simplifications. You can show that this is nothing but S contracted with F transpose F dot dV. But what is F transpose F dot? Right? We'll see what F transpose F dot is. Yeah. So we have this relationship F dot is equal to LF, right? Put this back. So S contracted with, we have F transpose F dot. In place of F dot, you put LF. Note that this is a symmetric tensor. So when a symmetric, so this is equal to S contracted with F transpose D plus W F. So this is nothing but S contracted with F transpose DF plus S contracted with F transpose WF. F transpose WF is a symmetric tensor. So this is take this transpose, you get F transpose W transpose F, which is minus F transpose WF. So this is a skew symmetric tensor. So this skew symmetric tensor contracted with a symmetric tensor is 0. So we are left with just this. So S contracted with F transpose F dot is nothing but S contracted with F transpose DF. But what is F transpose DF? To see what this is, we'll start with the material time derivative of the right Cauchy strain tensor C. So this is d by dt of F transpose F. So this is nothing but F transpose F dot plus F dot transpose F transpose dot, which is F dot transpose F. But F dot is equal to LF, so we get F transpose LF plus LF transpose F, which is F transpose LF plus F transpose L transpose F. Club these two, you get F transpose L plus L transpose F, which is nothing but 2 times F transpose DF. So F transpose DF is nothing but C dot by 2. Plug that into this. So this is nothing but S contracted with C dot by 2. So what do we get? We get an expression for the virtual internal work done in terms of the second Piola Kirchhoff stress S, second Piola Kirchhoff stress S contracted with half times C dot. So so this means the second Piola Kirchhoff stress S and half times C dot or work conjugate. Can we get something more intuitive than this half times C dot, because you don't need a half sign. So yes, we can do it. So for this, use the expression for the green Lagrange strain tensor. The green Lagrange strain tensor is half C minus identity. Take a time derivative on both sides. We get E dot is equal to half is a constant, C dot minus the time derivative of a constant is 0. This is nothing but half C dot. So in this you can replace it as S contracted with E dot dV. So we have got a third work conjugate pair, which is S and E dot. So to summarize, we have got three work conjugate measures. The first one is, let me use a different color. The first one is the work conjugacy between the Cauchy stress and the rate of deformation tensor. The second work conjugate pair is the Piola Kirchhoff stress and the material time derivative of the deformation gradient. And the third work conjugate pair is the second Piola Kirchhoff stress with the rate of the green Lagrange strain tensor. We can also derive more work conjugate quantities as follows. So we'll derive 3 more in the example problems that I'll be solving. So these problems are from Bonnet and Wood, the textbook Bonnet and Wood for nonlinear finite element analysis. Now this says show that with respect to the initial volume, let me use my earphones. There is some noise outside. I hope I'm audible. Yeah. Show that with respect to the initial volume, so with respect to which volume we have to say, one more thing. Sigma D, this is with respect to deformed volume, whereas we have these are with respect to undeformed volume. this one, and also we have one more, which is tau with t. So these are with respect to the undeformed volume V naught. This is with respect to the deformed volume V. So that with respect to the initial volume, the stress pi is work conjugate to the tensor H dot, where H is equal to minus F inverse transpose, and pi is equal to PC, which is J sigma F. So this may look quite hard to do it, but it's actually very easy. Let us proceed in the same lines. So it is given that it is with respect to initial volume. So let us start with a known pair of work conjugate quantities in the initial volume. What is it? Let us start with this S, and you can also start with P and F dot, but let us start with S and E, or S and C, right? So S is work conjugate to right. So uh, so they are asking us to so let's see which is easier, right? So this is yeah, you have a PC here. Okay, so let us somehow get PC in this, right? So this, what is S? It is F inverse P, or actually let me do one thing. Let us start with the expression for internal virtual work in terms of the first Piola Kirchhoff. That might make it simpler. So this is integrated over the initial volume P contracted with del F dot dV naught. Now we want to have a work conjugate quantity which is F inverse transpose, right? So so let us we are okay, sorry. Show that the with respect to the initial volume. So okay, we don't have to derive it. We just have to show that it is with respect to the initial volume. So basically, we have to show that this is equal to integrated over the initial volume pi double contracted with H dot. Right now, what is the this is simple. Let us start with the right hand side. It is integral over V naught pi double contracted with H dot dV naught. What is pi double contracted with H naught? H dot. It is PC. Pi is this PC double contract with F inverse transpose dot. Okay, so this is nothing but PC ij F inverse transpose ij. Get rid of the transpose, we get PC ij F inverse ji. Okay, so expand this out, you get Pik Ckj F inverse ji with a dot. There's a dot here. It's a dot, dot, dot. But F inverse dot is what? It is LF. So this is Pik Ckj LF Ji. Yeah. So this is nothing but, or let's do one thing. So let me just redo this. So we have the stress. We have to show that the stress. We have to show this. We have to show I have to show. So to show that pi and h dot are work conjugate to each other, we have to show that integral pi contracted with h dot dv naught integrated over, sorry, v naught integrated over the volume is equal to this p double contracted with f dot integrated over the volume. Right? So I start with the left hand side. It is, or just start with this quantity. What is this? Pi is defined as PC. So it is PC contracted with h dot. But what is h dot? It is PC contracted with F inverse transpose the whole dot. But what is F inverse transpose the whole dot? You can write this as PC. So the dot and transpose can be changed. So this is nothing but F inverse dot the whole transpose. Okay, so yeah, so this is fine. Have this as equation star. Now look at F inverse, F inverse. What is this? This is the identity. Take time derivative on both sides. We get F dot F inverse plus F inverse dot is equal to, this is a constant tensor, so its derivative is 0. So F inverse dot is equal to F inverse dot, it is equal to minus F dot F inverse. F is invertible, so I can take it to the other side. We get, sorry, F inverse dot is equal to F inverse minus F inverse F dot F inverse. But what we have here is a transpose of the same thing. So we have a transpose here. So transpose everything else. So we get a F inverse transpose, F dot transpose, and F inverse transpose with a minus sign. But what is F dot transpose? F dot is LF. Use that relation. We get minus F inverse transpose, LF transpose, F inverse transpose. So this becomes, right? So we are getting an expression for F inverse dot transpose. This is equal to, this is the last expression, minus F inverse transpose, LF transpose, F inverse transpose. This is minus F inverse transpose, F transpose, L transpose, F inverse transpose. So this is identity. So you get a minus F inverse transpose with multiplied by F transpose is, let me not skip any step. This F inverse, F inverse, the whole transpose multiplied with F inverse L, the whole transpose. So this is the identity. And what is this? This you can have it as it is. This is just F inverse L. Now plug this into the star, right? So we get pi contracted with H dot is PC contracted with a minus sign, minus of F inverse L. Okay, so yeah, so can we do something? Okay, so this further you can simplify this. So you write it as minus P. What is C? C is F transpose F contracted with F inverse L. Now we know that F dot is equal to LF, which means L is equal to F dot F inverse. So I can write that also. It is minus P F transpose F contracted with F inverse F dot F inverse. Okay, so this is fine. What is it we have to prove? J sigma F. Okay. Now see what this quantity is, right? So this is this you can retain it as it is minus F transpose F F inverse F dot F inverse. So this is basically the trace of minus the trace of P F transpose F whole transposed with F inverse F dot F inverse. So this is minus the trace of so let us see, is there any mistake somewhere? So this is fine. We start here. So this H dot, where H is defined as F inverse minus F inverse transpose. Okay, there's a minus sign that we missed here. So H is there's a minus already here. So here we have a minus sign, and here you have another minus sign. So this minus disappears. This is a minus. There's a minus here. So there's already a minus here. So that becomes a plus. So this is all plus. So one, yeah, that is fine. Then we have an F inverse transpose. F inverse transpose is this. So yeah, this is not, this you don't need to look at. Yeah, F inverse transpose. So it is F inverse transpose dot and transpose can be swapped. So it is nothing but F inverse dot transpose. And we find an expression for F inverse dot from this expression. So F inverse dot is minus F dot F inverse. And this F goes to the other side. So F inverse transpose is transpose everything minus F inverse transpose LF F inverse transpose and minus F inverse transpose. This is fine. This becomes an I and this becomes so this is the problem. So this is F inverse L transpose. That's the issue. Right. So here we have an F inverse L transpose. So here it is an F inverse L transpose. So this becomes transpose. So there is a transpose here. Yeah, now it is fine. So this transpose means you can just so this is equal to P F transpose F double dot F inverse transpose F dot transpose F inverse transpose. So this is PC double dot F inverse transpose, or actually this I should write it as L transpose F inverse transpose, then it makes it simpler. Okay. I just write this as pi contracted with H dot is PC contracted with, what did we get here? It is, there's a minus sign. Minus of L transpose F inverse transpose. Right? So this is P C contracted with L transpose F inverse transpose. Now you can use the initial notation. So pi contracted with H dot is nothing but P I K C K J. So this is P C I J multiplied with L transpose IK F inverse transpose Kj. So this is PIK CKJ. L transpose IK is LKI. F inverse transpose Kj is F inverse JK. So it is PIK LKI. This is fine. We have CKJ F inverse JK. But what is CKJ? C is equal to F transpose F. So CKJ is F transpose KL FLJ. So this is nothing but FLK FLJ. So you have PIK LKI FLK. So something is wrong here. So you cannot use the K again. Let us use M. Sorry about this. This is M. This is an M. Sorry, this is M. So this is L transpose IM F inverse transpose MJ. So L transpose IM is LMI. F inverse transpose MJ is F inverse JM. So here you have an JM. It is CKJ. It is L. CKJ, we just saw it is F LK F LJ. And here you have F inverse JM. So FLJ, F inverse JM. By the property of inverse, this is nothing but delta. The common index is J. So you get a delta LM. So you get FLK delta LM PIK LMI. So delta has the replacement property. So wherever you have L, you can replace it with a M. So this is PIK LMI FMK. So note M is repeated twice, I is repeated twice, and K is repeated twice. Therefore, we have a therefore this is a valid scalar. Now, as the last step, we have F dot is equal to LF, which means L is equal to F dot F inverse. So LMI is F dot MQ F inverse QI. So this becomes PIK. LMI is F dot MQ F inverse QI F MK. Transpose F. So we actually get this is we get a F dot MQ multiplying FMK PIK F inverse QI. Yeah. So here so better look at this stage. We have L, P, LMI, PIK, which is LP, MI. And what is the rest? Here it is, sorry, MK. This is LMI, PIK, which is LPMK. And here we get an F transpose MK. Okay, so this is actually LMJ, PJK, FKM. So this is F dot is equal to LF. So L is equal to F dot F inverse. So LMJ is equal to F dot MI, F inverse IJ. So this is F dot MI, F inverse IJ, PJK, FKM. So what I want to recover is P multiplied with something else. I want to get P separately. So let me have PJK as one term. What are the other terms which contain this? So we have an F inverse transpose JI, F dot transposed IM, and we have FMK, F transpose MK. Let's look at the next question. Maybe it's we'll get back to it. So using the time derivative of the equality C inverse equal to I, show that the tensor sigma, which is CSC, is work conjugate to half B dot, where B is minus C inverse. So okay, let us start with this. As they say, you start with C inverse is equal to I. What is take time derivative? So we get C dot C inverse plus C inverse dot is equal to 0, which is a tensor, which means C dot inverse is equal to, or minus C dot inverse is equal to, let me not skip any steps. So C dot inverse is equal to C dot minus C dot C inverse. I can take the C to the other side, which means C dot C inverse dot is equal to C inverse. You can take the minus to this side, C dot C inverse. So this is result 1. So what we have is B dot is equal to C inverse C dot C inverse. This is the first result. Next, they're asking us to look at sigma is CSC. Now let us look at this sigma contracted with half B. What it is? It is CSC contracted with half can be taken out. B dot is C inverse C dot C inverse. Now again, let me show a general result which can be useful for several problems, including the previous one where we got stuck. Okay. So the double contraction of a tensor AB with another tensor C is equal to B contracted with A transpose C. Let us see if this is true. So what is ABC? It is ABIJ CIJ, and this is AIK BKJ CIJ. Note that these two have I in common. So this is BKJ A transpose KI CIJ, which is nothing but B contracted with A transpose C. Similarly, look at the other result. AB contracted with C is also equal to A contracted with C B transpose. Same thing. This is AB IJ CIJ. We already saw this is equal to AIK BKJ CIJ. Look at these two. So you get it is AIK B transpose JK CIJ, which is nothing but AC A contracted with CB transpose. So have these two results in mind. This is say result A and this is sub result B. Now look at this. So this says sigma, let us call this 2. So 2 says sigma contracted with B dot is equal to CSC, sorry, sigma contracted with half B dot. So it is equal to half of CSC contracted with C inverse C dot C inverse. Now treat this as the tensor B and this as the tensor A. And this as the tensor, say C. So C contracted with AB is what? It is A transpose C contracted with B. So this is equal to half C inverse transpose C S C contracted with C dot C inverse. But now you can treat this as tensor A and this as tensor B and this entire thing as tensor C. So this becomes half. You can take this B to the other side. You get half C inverse C, C inverse transpose C, S C, C inverse transpose contracted with C dot. The half can be taken to the other side. So what do we get? We get sigma contracted with B dot, half B dot is nothing but C inverse transpose C, S C, C inverse transpose contracted with half C dot. But note that C transpose is equal to C, which means C inverse transpose is equal to C inverse, which means C inverse transpose C is equal to C inverse transpose is equal to identity. Therefore, we get sigma contracted with half B dot is equal to identity S identity contracted with half C dot, which is E dot. So this is nothing but S E dot. Therefore, integral over the initial volume sigma half B dot EV naught is equal to integral S E dot EV naught, which is the internal virtual work done. Therefore, the fifth work conjugate pair with respect to the initial configuration is sigma and B dot, half B dot. Now, yeah, so this problem where we got stuck, let us use this identity, right? Let us use these two results that we just got. The result of transferring transferring B to the other side and A to the other side. Sorry, A to the other side and B to the other side. So let's take a let's relook at this. Let me delete these. So this is the slide. So the question is this. So show that with respect to the initial volume, we have this. Let's take a similar approach. We have H is equal to minus F inverse transpose. So what is, start with F inverse F is equal to I. Differentiate on both sides. So say time derivative. We get F inverse dot F plus F inverse F dot is equal to 0, which means F inverse dot is equal to minus F inverse F dot F inverse. So this F I have taken to the other side, which means H dot, which is minus F inverse dot is equal to F inverse F dot F inverse. So let us call this result 1. Or let's call this result sum A. What is the next step? We have defined stress pi. Pi is equal to PC. We have to show that pi and H dot are work conjugate. This is what we need to show. So let us take this in a dot product. Let us take this contraction. What it is? It is PC contracted with H dot. What is H dot? H dot is F inverse F dot F inverse. So this is F inverse F dot F inverse. So what do we do? Is it PC? Yeah. So write this as PC contracted with F inverse F dot F inverse. C is nothing but F transpose F. So this is equal to J sigma F inverse transpose F transpose F contracted with F inverse F dot F inverse. So F inverse transpose F transpose is what? It is F inverse the whole transpose, which is nothing but identity. So this is nothing but J sigma F contracted with F inverse F dot F inverse. Now take this F to the other side. Using that second of the two relations that we just saw, it is J sigma contracted with F inverse F dot F inverse F transpose. So wait a minute. Transpose F. Yeah, this is all right. So this is fine. We get an F transpose here. Uh, or rather, okay, this is fine. This is fine. So this result, you can call this as this result, you can call it as result B. So we have on the left hand side a tau, and on the right hand side we have some combination of yeah, we have a certain combination of F, right? We have an F inverse, we have F dot, then we have an F inverse, inverse, and then F transpose. So let us see what to do with the right hand side. So we have on the so we have this F inverse, F dot, F inverse, F transpose. So this is nothing but F dot is equal to LF. So I have F inverse, LF, F inverse, F transpose, which leaves us with F inverse. What is LF? FF inverse is I. So we get F inverse L, F transpose. Okay. So note that yeah. So now note that F. We have something like pi contracted with H dot is tau contracted with F inverse L F transpose. So this is a symmetric tensor. This one we can't tell anything. This is neither symmetric nor antisymmetric right now. But we know that it will. This will when the double contraction with an antisymmetric tensor is going to give us 0, and only the symmetric part of this will contribute. Only symmetric part will contribute. So let us see what the symmetric part is. Mistake minus F inverse transpose. Okay, so here is a mistake. So H is a transpose of this. So there should be a transpose here. So there is this entire thing is transposed. So there's a transpose here. We get an F inverse transpose, F dot transpose, F inverse transpose. So here we get F inverse transpose, F dot transpose, F inverse transpose. Uh, and here we have F inverse transpose, F dot transpose, F inverse transpose. Well, let me again. Sorry, this is let me redo this, right? So this part is fine. This part can be redone. So H is F inverse. H dot is F inverse transpose F dot transpose F inverse transpose. So this is actually A. Finally, what do we have? We have to show that pi is work conjugate to H dot. So it is P C. So C is F transpose F is work conjugate to. What is H? It is F inverse transpose F dot transpose F inverse transpose, right? That's what we have. F inverse transpose F dot transpose F inverse transpose. You can use the transfer, push it to the left hand side of the double dot. So we get, we multiply with the transpose, you get FP F transpose F. What is this? F inverse transposed. So we get a F inverse double contracted with F inverse transpose F dot transpose. So this is just the identity. So we get a P F double contracted with F inverse transpose F dot transpose. But what is F dot transpose? F dot transpose is LF, the whole transpose. So you get, it is P F transpose dotted with F inverse transpose F transpose L. So we actually get, so P F transpose is what? It is J sigma F inverse transpose F transpose double dot with contracted with L. And this is J sigma contracted with L. This is a symmetric tensor. This has both symmetric and antisymmetric parts, but symmetric contraction with antisymmetric vanishes. So this is nothing but J sigma E. So this is the Kirchhoff stress contracted with the rate of deformation tensor, and therefore integral pi h dot dv naught is equal to integral tau d dot dv naught, which is the internal virtual work done. So therefore, we have a final sixth work conjugate quantity, which is pi and h dot. These two are work conjugate to each other. Yeah. Now we have another. We are going to show that the tensor T. So we are going to find which tensor. Right? We are going to, until now it was to show a given stress tensor is work conjugate to a given straight tensor. Here we are going to find a stress tensor which is work conjugate to the stretch tensor U. So this is interesting. Let us start with, so U dot is a strain-like quantity. Corresponding to that, what is the work conjugate measure? That's what we are going to find out. So let us start with C. C is equal to what? C is U square, or it is U dot U. Now what is C dot? C dot is U dot plus U dot U. So it is nothing but 2 times. Yeah, it's nothing. It's U dot plus U dot U. Now look at so T contracted with U dot should be equal to something. So this T contracted with U dot should be equal to S contracted with half C dot, because we know S and half C dot are work conjugate measures, work conjugate pair, and T and U dot form a work conjugate pair. So let us just substitute here. What is S double dot C dot? It is half S contracted with U dot plus U dot U. So this is nothing but half of S contracted with U dot plus S contracted with U dot U. So this is nothing but, again, this U can be transferred to the left side. This U can be transferred to the left side. Whenever you do it, take a transpose. It is half of S. This U is before, so it is U transpose S contracted with U dot plus S U transpose contracted with U dot. But U is a symmetric tensor, so U transpose is equal to U, which means it is half of US contracted with U dot plus SU contracted with U dot. So U dot is common. You can take this out. It is half of SU plus US contracted with U dot. Compare both sides. We get, what do we get? We got T contracted with U dot is equal to half of SU plus US contracted with U dot, which means T is equal to SU, half of SU plus US. So this result we can also verify with the one given in the book. It is correct. Now further you can write S F inverse P. So T becomes half of F inverse P U plus, or rather, instead of making the substitution on S, let us say F is equal to RU, which is polar decomposition, which means U is equal to R inverse F. So T is equal to half SU, which is S R inverse F plus U, which is R inverse Fs. Note that Fs is equal to P. And here what do we have? It is half S is J sigma F inverse transpose R inverse F plus R inverse Fs, which is P. And R inverse is R transpose. So this is equal to R transpose F. And here you have this quantity, which is F inverse transpose R inverse is F inverse R transpose. Sorry. So this is actually F inverse transpose R inverse. This is R F inverse the whole transpose. Yeah, so the rest you can just and see what P transposes. P transposes J sigma F inverse transpose the whole transpose. There's no minus here. So this is F inverse sigma J F inverse sigma. So what is R F inverse? So F is equal to VR, which means F inverse is R transpose V, R transpose V. So F inverse transpose R inverse is equal to R transpose V. I can put a transpose here and an inverse here. The whole transpose. So this becomes V transpose, which is just V. Anyway, let's that you can show, and let's look at this. Yeah, so this is a problem in decomposition of the stress tensors. So we know that sigma can be decomposed into two parts. One, which is hydrostatic plus a deviatoric part. So the deviatoric part is nothing but sigma minus half trace of sigma. Sorry, 1/3 trace of sigma. So this is called the hydrostatic pressure P. So sigma is equal to P times I plus sigma dash. Similarly, we can also show that the first Piola-Kirchhoff stress is something plus a deviatoric part, and this will be deriving from this. Similarly, the second Piola-Kirchhoff stress is also something plus a deviatoric part. Now, essentially, the trace of P dash and the trace of S dash are not necessarily zero. They are not truly hydrostatic. They are not truly deviatoric in the sense of sigma, but they are derived from a deviatoric part of sigma dash. So we define P dash as J sigma dash F inverse transpose. So P dash is the Piola transform of sigma dash, and S dash is the Piola transform of is F inverse times the P dash. So this should let us know what uh, P in terms of P dash is. So P is equal to J sigma F inverse transpose, and P dash is J sigma dash F inverse transpose. But what is sigma dash? It is J sigma minus half 1/3 trace of sigma I F inverse transpose. So this is J sigma F inverse transpose minus 1/3 trace of sigma J F inverse transpose. So this is nothing but P. Therefore, P is equal to 1/3 trace of sigma J F inverse transpose plus P dash. We already call this as P. Therefore, P is equal to PJ F inverse transpose plus P dash. Now, we want to find an expression for this small p in terms of the total the total Piola-Kirchhoff stress P. So let us do that. So for the first part of the answer, it is this, right? So by definition, P is nothing but 1/3 trace of sigma. So it is 1/3 trace of sigma is sigma double dot identity. So this answers the first part. For the second part, let us see what we can do, right? Now look at this P dash and dot product it with, or contract it with uh, F. Right? Yeah. So look at this P dash and contract it with F. So we get so P dash contracted with F is J it is J sigma minus. So this 1/3 trace of the, I can call it as small p I F inverse transpose contracted with F. So this F inverse transpose can go to the other side. You get J sigma minus small p I contracted with F inverse. So F inverse is I. So it is nothing but trace of. So you get J sigma minus p I contracted with I. What is I contracted with I? I contracted with I is 3. Sigma contracted with I is trace of sigma. So you get J trace of sigma minus 3 times P. But what is 3 times P? This is equal to trace of sigma. Therefore, P dash contracted with F is 0. So this is one orthogonal relation. We also know the other orthogonal relation, which is sigma dash contracted with I is equal to 0. So the trace of the deviatoric tensor is 0. And we have S dash contracted with say C, right? What it is? This is F inverse J F inverse sigma minus Pi F inverse transpose contracted with C. C is F transpose F. Take everything to the other side. So you get J sigma minus Pi F inverse transpose. You get an F inverse transpose F transpose F inverse. This is basically I, and this expression is the same as this one. So this is 0. And the third expression is S dash contracted with C is equal to 0. Now these three expressions give the conditions for finding P in terms of P dash and S dash. So use the first relation. We get sigma dash contracted with I is equal to 0, which means sigma minus P times I contracted with I is equal to 0, which means P is equal to, so this becomes 3P is equal to trace of sigma. So P is equal to 1 by 3 trace of sigma. The second condition, we have P dash contracted with F is equal to 0, which means P minus, this has to be just P times I. So the hydrostatic part does not change in any case. P minus Pi contracted with F is equal to 0, which means wait a minute. No, it's not Pi, it is P. What did we have here? So it is the Piola transform of the stress. So it is P minus J P F inverse transpose double dot with F is equal to 0, which means P contracted with F is equal to J P F inverse transpose contracted with F, which is nothing but J P I contracted with I. Therefore, it is 3JP. So the pressure is pressure in terms of P is 1 by 3 J inverse F contracted with P. Now, in terms of S, it is even easier. So we have P is equal to 1 by 3 J inverse of F contracted with P. This is one relation. Now we use the orthogonality between S bar and C. This is equal to 0, which means S minus, what do we have here? S minus the pullback of Piola transform of pressure. So F inverse of, what is the Piola transform of pressure? It is JP F inverse transpose contracted with C. What is C? C, let it be C only, is equal to 0. So which means S contracted with C is equal to F inverse J can come out, P F inverse transpose. So to carry these to the other sides, you get wait a minute, F inverse transpose contracted with C, which means S contracted with C is J. Here we have an F transpose F, so you get F inverse P, F inverse transpose F transpose I. So this is identity, this is identity. Therefore, S contracted with C is J P I contracted with I, which is nothing but 3. So P is also 1 by 3 J inverse of S contracted with C. So these are precisely the relation here. So it's 1 by 3 J inverse S contracted with C, 1 by 3 J inverse P contracted with F, and it's also 1 by 3. There's no J inverse. This is all material descriptions, and in the spatial description, it is 1 by 3 sigma contracted with I. Or it's also 1 by 3 J inverse tau contracted with I. So we are out of time. That is basically the end of today's session. I also had another section on objective stress rates, but we don't have time. But there are no questions based on that. Maybe we can take this up in the next session. So thank you, everyone. I'll end the recording here.